It's time. So, ladies and gentlemen, hope you've been enjoying the talk so far. And our next speaker is Gabriel Claramunt. He comes from Uruguay. He is the founder of Scalents, a Scala consulting company focused on using Scala and functional paradigm for all the good stuff. Big data, machine learning, you name it, they do it. But he's not only an accomplished businessman, but also a seasoned computer scientist. His LinkedIn profile page scrolls ad infinitum. And speaking of ad infinitum, his talk will be about maths in programming. He's going to take you on quite a trip through the land of Lambda calculus, Curry-Howard isomorphism, Kurt-Gödel's incompleteness, category theory, not only for you to admire the elegance of mathematics, but also to solve the real programming problems. So please welcome Gabriel Claramunt. Gabriel, the stage is yours.
Thank you for the great introduction. First quick question. Is everybody looking okay? You can hear the audio, you can see the slides.
It's okay for me.
I take your word for that and assume that everybody's
looking at the chat. No one's. Yeah, people are saying it's okay. So
perfect. So let's get started with this. Okay. If you want to introduce me, just type the question or whatever. I'll take a look. Thank you all for coming to this conference. It's looking great, and thank you for coming to this talk. Hopefully it's fun. The idea is to talk about the unreasonable effectiveness of mathematics for computer programming. And first, as a disclaimer, this story is based on actual events. Certain cases and incidents, characters, or timelines have been changed for dramatic purposes. That means I might get some facts wrong. I'm happy to correct it later, but the whole idea is to have something fun. This idea is based on one famous article or paper that's called "A Reasonable Effectiveness of Mathematics in the Natural Sciences." That starts. It starts mentioning why, trying to figure out or explain why mathematics is so effective for natural sciences. It starts with pi. You have pi, that is just a relationship between the radius and the perimeter of a circle. But then you see pi in the standard distribution of probability. It's something that describes a population and describes pretty accurately. But what have to do with pi? And then it goes out with this this formula describes pretty correctly the population. And then it talks about also Newton's law of gravity, that based on a few data points and the formulas that Newton kind of discovered, it can predict pretty accurately the position of the planets. Also, it's a funny story that it kind of follows what we're going to try to do, but for the quantum mechanics, when they derive the equations, basically they took the normal movements law and replaced variables with, instead of variables, with matrices, and then all the equations were kind of correct, but just using matrix calculations. But the thing is, all this started like a pure abstract mathematical pursuits, and then it ended up like describing pretty accurately the real world. But what about programming? We are here for about programming, right? First, let's tell a story. It was the beginning of almost the beginning of the 20th century. We have Whitehead and Russell wrote a huge book called Principia Mathematica. They try to define the whole body of mathematics using formal logic. It was great. It was a great idea, trying to have like a formal language to describe all this kind of. They were doing things rigorously, but nobody has tried to really figure out what's behind that. So they started describing mathematics with a formal logic. And inspired with this, Hilbert and his colleagues in Göttingen they were like the leading proponents of formal logic. They were trying to put mathematics, that's a reasonable pursuit. They had trying to put mathematics on something firm and some formal and formalized, some formalized basis that we can build. So they have like three major goals, like prove that that formalism they trying to create has no contradictions. They were trying to prove that all true mathematical statements can be proved on that formalism, that is the completeness, and the decidability. That means they have a way to tell if a statement was provable or not. Basically, that is called the Entscheidungsproblem. They have three major goals for that. So they have trying to formalize mathematics with these three major goals. And as late as, with the same optimism we started 2020, Hilbert believed that it couldn't be such a thing, that a problem that mathematics could not solve. But Kurt Gödel had bad news for them. Kurt Gödel, it was a young mathematical genius, and he has this knack for proving other people wrong. He wrote the first incompletement theorem that basically says any formal system complex enough just to have like a basic arithmetic, there were statements that you cannot prove or disprove. You cannot prove true or false in that. So there goes the first goal of Hilbert. Then he wrote the second incompletement theorem that if we assume that we have a this formal system we were to try to explain mathematics, if it also again contains something as basic as just basic arithmetic, you cannot prove that is consistent within the system. Basically, if you cannot describe the consistency of the system with you cannot prove the consistency of the system with your own logic. So let's go the second goal of Hilbert. So the only thing they got left for these guys was the Entscheidungsproblem, the decision problem, that is create a method that is effectively calculable to prove the true or false. And here we start to get into the core of what we do, because effectively calculable means basically you can write a program. But for at this time of at this age, it wasn't really something they could describe. So they have this guy, Alonso Church, in Princeton. He was trying to find a solution for that problem, and invented a formalism to basically prove that you cannot do that. Also bad news for Hilbert, but Alonso Church, to prove that, invented create something that he called the Lambda calculus, to prove that you cannot have an effective method to decide that any theorem was provable or not. Again, it came Kurt Gödel. When that was presented, he was also there in the seminar, and he didn't like it at all. So he went again to do the same thing using formalists he called recursive functions. And this guy, it was in Britain. The also was working on the same thing, and the formulas he created to prove that was he called it like logical computing machines, the thing we know as Turing machines. All the 3 different ways to prove that the Hilbert was not was wrong, but couldn't do what he wanted to do. Yeah, this is the original paper of Turing, and they keep the computable numbers with application to the Einstein's problem. And here introduce the Turing machines. So Kurt Gödel took a look at the Turing machines and really like it. And for us, even Turing machines, after they were created, it was a really useful model. It was easier to understand than lambda calculus. Lambda calculus is just application and abstraction of just kind of, if you want to think, strings, just for manipulation with formulas. But this Turing machine was more easy to conceive as a real machine, something working. You have a long tape of symbols. You have one state machine that reads and writes and go back and forth. Actually, it was easier to translate to a physical machine. I mean, you can see around tutorials. You can create a Turing machine with Lego and a reader. I mean, it's way harder to create like a lambda calculus interpreter. So it's natural that computers, when we create the computers later, were based on the Turing machine paradigm. But the Turing machine has this problem that at this point, programming in the Turing machine model is harder. I mean, you have state, you have so Turing machines are harder to compose. You don't have a way to see how they compose. So we are, as we move to functional programming, we are moving on something based on the lambda calculus. So let's take a look at that. The whole idea, it was take a formula with some variables, abstraction variables, and start replacing values with application until you get like just operations and numbers and get the final number. That was the original idea. Even incidentally, the lambda here is just an accident. The idea, they wanted to have a hat like I have for the exponential. But when they tried to typeset that, they didn't have it, and the closest thing they had, it was this lambda. So even the name itself is just an accident. The idea of the lambda calculus is something as simple as possible. You have variables, you have abstraction where you have one variable that later will be replaced, and you have application that basically takes every instance of that variable and replace it with the value you give. Only with this, we are able to computate values. We have a kind of a programming language, if you want. And for a little more formal definition, you have any term of the lambda calculus is either a variable, abstraction that is lambda variable of a term, or application that is term 2 applied to the variable, the first variable in the term 1. And basically the main mechanism of computation is what is called like beta reduction, that you take every occurrence of x and replace with n here. With that, you can do a lot of things, even if it seems pretty primitive, but you can define, but just by application of functions, you can define numbers, like 0 is no function, 1 is the function applied once, 2 is a function applied twice, 3 is a function applied 3 times. You can define even some, you can define true or false Boolean constants. You have your Boolean combinators like and, or, not. Even you can define if, just by application of functions. Actually, all this, it might, you can have some use for this. It's called like charge encoding of numbers and booleans and everything. Even you can have like a recursion defined in the Lambda calculus, the famous Y combinator, when you give a function and basically it recursively apply that function. That's to show to, even with something very simple as variables application and abstraction, you can have a lot of things. And even with only these very few things, you can create an actual programming language. The first language is not really a direct application of Lambda calculus because it has state, the initial implementation has state and everything, but it was pretty close. It was a very minimal language, and you can do a lot of things with Lisp. Even there is, as you know, later they created like a scheme that is a kind of a more functional Lisp that is basically an interpreter for extended Lambda calculus. If you saw scheme, it has mostly like you have application, abstraction, and very few more things. All the rest is like can be considered syntactic sugar. By the way, this is a little book about scheme. I couldn't read anything about scheme until I got this small book that is really fun to do it. So I recommend everybody that book. It starts from very, very simple things and it goes, then it takes you to write the Y combinator. You prove the Einstein's problem here. It's very fun. But Lambda calculus alone is too simple. And we want to have more to have more formality and be more sure of what we write. So let's talk about a little about types. Types, again, are something the mathematicians invented for tackle some of the paradox in set theory, like the Ross's paradox. If you didn't hear about that, is something about you have a library. You have a country with libraries. Every library has catalogs with other books. Some catalogs include the catalog itself. Some catalogs doesn't include the catalog itself. But now you have your master library. You have a catalog of all the books in your country, and now you create a catalog of catalogs. But what if you want to create a catalog that doesn't include a catalog of all the catalogs that don't include the catalog itself? You cannot create a catalog because otherwise it don't belong to the category. You cannot include it in the catalog, and then you have to include it, and then if you include it, don't belong, and you get in this endless loop. So set theory wasn't enough. That's why they elaborated like type theory. And one way to elaborate that was to extend the Lambda calculus with types, especially because with types, without types, with Lambda calculus, you get things like this delta combinator. Basically, it takes an x and applies x to x. What if we apply that twice? You replace the delta with the definition. But then if you apply all the rules and evaluate the result in lambda calculus, you end with the same thing, and then you have to apply again. So it means it doesn't reduce; it's reduced. It never terminates. That's a problem if you want to have a decidability. If you want to make sure that everything gives you a result. So we have this guy who extended the lambda calculus without simple types. Basically, it's the same thing as the original lambda calculus in name of terms. It just added constants. Constant is just something to make things easier. But now every term on the lambda calculus has a type. The types are either the type of the constants or the type of the functions. That was formalized. All this was formalized at Haskell query. And the idea, you have the same thing. You have abstraction and application with, but with also everything is type. So application, you have an n that goes from A to B, and an m that has type A. So the application of m to n gives you a B. An abstraction, if you have an m of type B and you're going to abstract on an x of type A, you end up with the lambda x of m that is the type I from A to B. The good thing for this is that why they created this is strongly normalized, means always terminate. You don't have formulas that never reduce. Especially because when you try to type the delta combinator we saw before, like x applies to x, you cannot write the type for that. Basically, it doesn't type check. So it means all the type line model calculus programs always terminate. That's a very important property. But there's another extension. Once we have the type lambda calculus, we want to do more things with that. So there's this thing called the polymorphic lambda calculus, also called system F. And the interesting thing again is this was first discovered or kind of created by Jan-Yves Girard to describe the second order, higher order logic. Basically, is we're trying to express logic with the type of lambda calculus, and he extended this to a higher order. And the same thing in parallel with, not in parallel, but later, without knowing that was discovered or created by Reynolds, when basically we try to define parametricity, not parametricity, but he created an extended lambda calculus that you can use basically generics. This is right now we're using something like that. We call it generics because it means the types can vary also. It's like a lambda calculus for the type system. And it's the basis of ML, all the family of ML, standard ML, OCaml, and also Haskell. This Haskell, it has something like we call almost like an assembler, Haskell assembler, but it's not really assembler. Basically, you can desugar all your Haskell program, and it gives you system F. Basically, it's like a simple, it's a polymorphic lambda calculus. And that is the idea, the same way that Church and Turing, they were not trying to create programming languages. They were trying to write like they were working on the logic of mathematics, but we take those ideas and apply it almost directly to computation, to writing programs. For me, it's almost amazing. If you go to church and they say, okay, I'm going to use your formalism you invented to prove this weird, pretty abstract thing, I'm going to use to just to write programs, to use it for everyday things. I think it will be pretty amazing. First, it will look you as, are you crazy? This is something that is totally abstract and not practical. Don't you dare to do something practical with that. But I think probably it will be like, after I think about it, will be amazing. The Turing machines is maybe more conceivable because itself, the concept, it was more like a machine. It was easier to think, okay, we can build that. But all this goes to show that there is a kind of an underlying connection between logic and computation, that we're like running around looking in from different sides to the same thing. And if we take a very simple program, function application, this case, this kind of Scala syntax, but you take a value of A, you get a function that goes from A to B, and if you apply the function to the value, you get a value of B. That's from the point of view of what we write every day. So if we go, if we take from the running program, you get an F, you have an X, you apply X, F and in X, and you get the value, the final result. But let's look at from the types. Let's view it from the point of view of the types. You have an A, you have an A to B, and the result is you have a B. And this looks a lot like a modus ponens. This is just basic logic. And that's kind of the observation that took to the Curry-Howard equivalence or isomorphism. And this is one of the, I think it's one of the most fundamental things we got lately. The idea is that started with Curry discovered a correspondence between the duplication of intuitionistic logic and the simple type lambda calculus. Intuitionistic logic is this constructive logic. Compare that, they were like very similar. Howard extended that to first order predicate logic. And then it turns out that the corresponding in intuitionistic type theory, that is one of the logic models, there is an identification like proposition and types. Propositions are types, types are propositions. And that's a huge stepping stone. And it's more like, initially it looks like it's just a syntactic thing. It just looks similar. But there is a very strong mapping, even in the application rules and different rules. So basically, we are really looking at the same thing from a different point of view, either from the computational programming side or the logic side. You can get a mapping for almost interesting things like quantification, universals and existentials. The implication, as we saw, is the function type. The conjunction is the product type, what we call like product type. Is the disjunction is the sum type. A true value is a unit type because you can return it from anywhere. The first formula is the bottom type because you cannot create it. On the logic side, you have hypothesis. On the programming side, you have like free variables. Any parameter you take in a function is kind of a hypothesis and assumption. you have one. You have an implication and elimination, less application and abstraction. But basically, it's all things. We are mathematicians, logicians, and programmers are kind of talking about the same things, but from a different point of view. But here, what we are saying that a proof is a program, and the formula that it proves is the type of the program. So when you write the types of a program, you're writing you're writing a kind of a theorem, and when you implement it, you're writing the proof. That means like proof can be run, and that is the basis, the whole idea of all these new like theorem programs and dependent types programming languages like Coq, Iris, Agda, when you can use this system of programming languages go in the middle line that you can use it as a theorem provers from the logic side, and you can use it as the programming languages from the programming side. Most of them are like are total. I mean, it means you don't have a program that never terminate. You can prove that every program terminates. They are not Turing complete, but they can go very, very far. And since you are writing programs that are proofs, if you can prove that your program is correct without even testing it. So we almost we after these kind of things, we can say there is a very strong equivalence between logic and computation, between programming and writing theorems, and it's a huge concept to exploit even in programming languages that are not total. You still have your type system that basically is a way to write theorems and write properties about your code. And also, as a side note, since we have a little more time, there is more. I'm not going to do this in detail. We can add category theory to the game. Category theory is, again, another weird mathematical theory that they created because basically there were this they were trying to formalize natural transformations, and to formalize natural transformation they have to invent functors, and to explain functors they have to invent categories. They went backwards. But again, category theory is something very simple about. Basically, it's the theory of composition. If you want to take away something, when you have things and connection between things, and there is no syntactic equivalent like the logic and the typing, the Lambda, the typing side, like the Corey-Howard correspondence. But you can define a category concept for every concept in the Corey-Howard equivalence, and then that's the extension did by Lambda. So you have logic, programming, and category theory, all things that they model the same thing. And I found a very interesting note about Robert Harper, one of the main workers of ML, that kind of jokingly talks about the computational trinitarianism in the same way that some religions, you have the Holy Trinity, that you have three things that are different but are the same thing. He talks about the same way about logic, languages or categories, whatever is your focus, you're kind of talking about the same thing. And it's very powerful being able to look at the same thing and from a different angle and apply all the kind of a formalism and knowledge from other sides to get like a better result, right? We can now take things from logic, take things from category theory, and basically apply it to our programs. Or in the same way, all this, now the logicians can use theory improvers because we can write a language that basically implements the logic and runs it. And I think all this, is really, really powerful and really interesting and fascinating. And I just hope I was able to convey a little why it's so interesting. And thank you.
Thank you very much, Gabriel. Thank you. Everyone is clapping in the confines of their homes. You can only hear me, but that was really great and fascinating talk. There are no questions in the Q&A center, so I take the liberty to ask my own question, because I was wondering, where does the incompleteness theorem, not having a term that's provable to be, well, true or false, where does it show in lambda calculus? How does it manifest itself in lambda calculus?
If I recall correctly, there are because actually I think I read the paper, but it was long time ago. I think there are like the combinators are never reduced when you try to you apply the rule.
So something like omega that's reducible. That makes
it will never. It's the same as because you are trying to prove that you cannot say that every program will stop. Same because the Einstein's problem is the same like the stop. And in the Turing way was we create a Turing machine description.
Universal machine, yeah.
Yeah, and you tell the machine to analyze the actual description of the machine, and there is a proof that you in the same way. I mean, it's easier if you do it with programming languages, right? When you say, okay, if I can write a program that giving any program will tell me it will stop. What if I give that program, the program itself, but with the value switched? If it stops, it return false. It will never stop, and if it will not stop, it will stop. And you find a way that you never find a way to grade that. But I don't remember exactly the text, but I think it's that if you have a formula that never reduces, you cannot stop.
That makes sense. Yeah, thanks. Also, I love the comment about the Haskell's assembler. That really got me. So where does for instance, things like type classes, where do they fit this picture of? Because I don't think they fit the picture of system F or F omega, right? They are somewhere beyond that. What's your take on this?
I don't remember. I think probably we have to go as all things Haskell. You have to go to the original paper, and I don't remember. But I think it was just something that they come up so they can have like different. I don't know, like extend the normal types. Yeah. But probably.
Yeah, definitely. But I think my question is about how does that correspond to Curry-Howard? Where does that fit the logic equivalence, the logical equivalence?
Yeah, I don't have it at hand, but it's basically you're kind of creating subsets of types. But it's something like that. But I don't have the details. Probably we have to look at it later.
That's easy to understand operationally, right? But in terms of Curry-Howard isomorphism, I think I'm lost. I don't know how it fits the.
It probably corresponds to a different order of logic, where you have the universe of types, and every type also you kind of have a subset of those types. You have like a filter of the types. I'll say, okay, this.
Yeah, but that's an operational view, right? But what's the static, the notational view of that? I think was my question. Yeah, but that's certainly something to look into. So once again, we don't have other questions. I don't have other questions. So once again, thank you for a wonderful and very, very interesting talk. I'm clapping for you.
Thank you, thank you.
And for all our panelists and you, if you want to hang out with Gabriel, there is a link I'm posting here in the group chat. That's the link to a breakout room where you can hang out with speakers, with Gabriel, and well, ask more questions or just just hang out together. Gabriel will be there shortly, and